Hi, in this lecture, we're gonna discuss stacks. Stacks is another data structure that's used widely in many different kinds of applications. We'll see some examples towards the end of this lecture. What's a stack? A stack is data structure in which elements are added and removed from one end only. So basically, a stack operates in a way that you can only add or remove elements from the top. And this data structure is called a last in, first out, just because that action of adding or removing is from the very top of it. So it's called a LIFO. And the primary operations on the stack is a push and a pop. Push is to add an element. Pop is to remove an element. Here are some real life examples. We may have stack of coins where you remove or add coins from the very top only. At the bottom, you don't change. Similarly, you have a stack of trays, stack of boxes, or books. Now here's a representation of an empty stack. So we have 5 elements that are waiting to be stacked. Now here's a kind of a simple process to look at, the stack operations. We may push a box A to the empty stack, and now it has 1 element. Then we'll push box B on top of it and push C. We can retrieve the top element. That's, by picking at it, but we're not moving or adding. And then we may push another element, D. And then we may pop that element off, and now we're back to C. So there are a couple of stack operations. If we define stack as a ADT and initialize the stack, checking if the stack is empty, maybe the stack is full, push and a pop, and also we may peek at the top element. Now, there are a few different ways to implement this stack. First way we're going to look at is to use arrays as the backend data structure. So basically, the idea is if you you push at elements, the first element goes to the first array position, second goes to the second position, and so on. And then the top of the stack is the index of the last element added to the stack. And the stack elements are stored in the array. Now, as we know, array allows random access. The stack element is accessed only through the top. Now we need to keep track of the top position. To do that, we can use a variable called stack top. Now the stack, since we're using the array, so we need to allocate the array. And when you do that, you need to specify the size of it. So with an array, your stack has a fixed size. you know, maybe you have a stack that you declare, they say you know, allow 100 elements, and then you actually initialize an array with a size of 100. Then let's say we call this implementation of stack using array as a stack type, and the stack type implements the the functions of the stack.te abstract class. Here's what stack type may look like in a class definition. So we want to maintain a couple of variables. We want to know what's the size of the stack. Essentially, that is the size of the backing array that's used to store the elements. And then we'll need to keep track of where the top of the stack is, which is just the index of the array. Well, not exactly. The way we're tracking this thing, if it's pointing to, if this stack top is 0, we want to say the stack is empty. So if this is a 1, it's pointing to the array index 0. The first element of the array is a 0 based. So there's a little difference here, the way we implement this typically. And then we have some of the typical, now, some of these operations, obviously this is coming from the stack ATT. And then we have a couple of typical operations. We want to override the assignment operator because we have a raw pointer member variable, and we want to have a sort of a deep copy operation, sort of a shallow copy. And then we may use a private function that does the copy, because this will be used for both of the assignment operator as well as the in the constructor that we initialize a stack type with another one. And then we may have a destructor. So what we just talked about, the stack top, we want to say if the 0, stack is empty, and the top element is at the index stack top -1. So there's some, here are some examples. Let's say I have a stack that's backed by the array of 100 elements. Well, the array size is 100, but we may not be, so the actual stack size is gonna change. So in this particular example, we have 4 elements in the stack. And this is, this array is pointed to by this basically a variable. Now remember, the array element, the name of the array is essentially a constant pointer to the backend, to the array. So that's why it's represented as an arrow here. And now stack top is 4. Essentially, that's the number of elements in the stack. So 4 minus 1 is index 3. That's how you retrieve that top one. The stack size is the size of the array that we allocated. So initially, when we initialize the stack, we are not using the array. So the stack is empty. And the stack top is 0, no elements. So when it comes to the implementation of the actual functions, so the condition to check if the stack is empty, we just compare the stack top with a 0. If it's a full, means the stack top is the same as the maximum stack size, or the size of the array. When we want to push an item to the top of the stack, we will move the stack top, by one more position. So we increment that value. So if we have a full stack, and then we can no longer push a new item onto it, that's the overflow condition. Now, let's say before we push an element, right now, currently we've got the stack of, of 4 elements. And then we want to push another element, y, to the top. So now the stack top is incremented by 1. So now it's 5. It's 5 elements in the stack. To get the top element, so essentially the index is stack top minus 1. Then we retrieve that element from the array, and that's your top element. To pop an element off the stack, we decrement stack top by 1, moving that stack top down from the stack. If the stack is already empty, we can no longer remove an item. So that's an underflow condition. Here's a visual representation. So we got a stack of 4 elements. Then we're gonna pop the top element. We'll simply reduce stack top by 1. We don't need to erase or change this value. We're just not using it. Next time, if we add push more element onto it, then this value will be overridden. So just, abandon that element. Copying stack is also pretty straightforward. First, you want to just, deallocate your current backing array. And then you copy the some of the variables, such as the max stack size and the stack top. Then you allocate a new array, and then copy the content of the array from the other stack. Constructor, we simply set the stack top to 0. The stack size will be some kind of default value or a value that's provided. And then we simply create the array. And then destructor would deallocate the array and the stack top back to 0. Copy constructor is essentially the same thing that we just saw to copy a stack. To overload the assignment operator, because we got some raw pointer as a member variable, we need to take care of the assignment operation. So essentially, we just invoke that private function copy stack that gets the job done. Now, we can also implement stacks with linked lists. Now, why do we want to do that? Because if we use an array has to be allocated with a fixed size. It cannot be changed. So that stack has a capacity. Now, if you want a stack that just grows as much as your memory allows, and then you may use a linked list. In that case, the stack top is going to be a pointer to the top element of the stack. Let's take a look at this example. An empty stack, you have no elements. The stack top points to no pointer. If you have a non-empty stack, let's say we have 3 elements here, then the stack top points to the top element. Now, if you imagine you turn this representation counterclockwise by 90 degrees, this is a linked list. Essentially, stack top is pointing to the head of the list. default constructor, we just initialize stack top as the null pointer. And the empty stack condition is that if stack top is null pointer and then it's empty, well, since it's a linked list, the stack cannot be full. Practically speaking, it's just, you can grow as much as your memory allows. Initializing a stack to an empty state, you basically deallocate the list if you have anything there, and then you set the stack top to null pointer. We're pushing to push in a node or element onto the stack, you first, remember the stack top points to the top, and then you create a new node. You want to push this onto this stack. So what you do is first you kind of insert that new node into the linked list. It's the new head. Then you move the stack top to that new element. Then basically now we'll push this new element onto the stack. To return the top element, it will essentially retrieve just from that stack top pointer. Now, how to pop an element off of the stack? So before the pop operation, we have, the stack top always point to the top element or the head of the list. And then here's the process looks like this. So you can, you create a temporary pointer that points to the very top. And then we're gonna move the stack top down following that link, the next variable of that element. So you move on to the next element as a new top. And then you just delete the top element. Then you have a new stack. The top element was popped off. To copy a stack, this is just essentially the same thing as copying a list. So here's what it might look like. If you want to have a copy constructor, you just use that copy stack operation. You set the stack top to null pointer. Destructor, you just initialize the stack again. To overload the assignment operator, again using the copy stack function. That's what is involved. We can also implement this linked list stack by deriving from unordered linked list. Now, remember unordered linked list, what we learned in last week, it supports operation called insert first. Essentially, you always add new element as the new head. And as we just learned, the head of the list is essentially the top of the stack. It just turned 90 degrees to look at that way. Many of the functions are actually similar to the list, so implementation is trivial. And then linked stack type, you could potentially just derive from linked list type as the abstract ADT. Then you just have to implement those functions. But then it would be easier if you just inherit from the unordered linked list type. That's a concrete class. Then the implementation of this stack on top of this list is trivial. Let's look at an application of the stacks. This example is called a postfix expressions calculator. So what is a postfix? Now to understand postfix, first let's talk about infix. So infix is actually the usual notation for writing arithmetic expressions. So essentially you have a operator that's in between two operands. When you look at a plus b, this is called an infix notation. Now, this expression will be evaluated from left to the right. The operators may have the precedence, and then you may use parentheses to override the precedence. Precedence means which operator gets calculated first. Then we also have the prefix notation, or is also called Polish notation. Now, with that notation, you have the operator before the operands. When you do it this way, you don't have to have parentheses. Now, the case we're looking at is the reverse Polish notation. This is also called a postfix notation. In this case, the operators follow the operands. Now, the advantage of this is operators appear in the order required for computation. Now, let's look at an example. A plus B times C. When we rearrange this in a postfix format, it will be A. So essentially, it's like you have the operands A, and then you have B and C. You have to multiply B and C first. Once this is done, so when you encounter this operator multiplication, then you retrieve the two operands right before it, and then you calculate this. So this becomes a new operand for the new operator. Then next thing you encounter is the plus. So you add this new operand with another operand A. So this is how you calculate with a postfix expression. So here's a couple more examples. Now the infix expression is what we know. C is in the programming language, such as C++. And then when it's arranged in the postfix format, A plus B becomes AB plus. So your program is going to read this, encounters A, and then B, and then encounters operator, and then it's going to calculate this and then becomes a new, basically a new value that will be used in the further operations. And then A plus B multiplied by C, and then that's what we just explained. Now let's take the last example, A plus B, parentheses, multiplied by parentheses C minus D divided by E, and then that whole result plus F. So since they're complicated, then let's look at this transformation here to postfix. First thing we want to do here is to do this sum of A and B, the addition. So what you do here is AB plus. When you encounter this operator plus here, it's going to evaluate A plus B. This is 1 unit. You've done this. Now the next thing is this second term here. So to calculate this, well, you put in C, you don't do anything yet, and then you do D, E, and then you have a division. And because we need to calculate D divided by E first, and then the result of that will calculate a subtraction. This is subtracted from C because now we see a minus. Now this whole term is parenthesized. So then we have multiplication. So the next operator is multiplication. This new value, remember the first thing we calculated A plus B. So these two terms now will be multiplied. Okay, so now we got the first big portion done. And then what's left, you have an F, and then you have an operator plus. So that whole result up to this multiplication will be added onto F. So that's the postfix format expression. Now, why do we do postfix? Postfix is important. Now, as I was just kind of alluding to, that in a programming language, we write an expression, in this case is a arithmetic expression, in the infix format, because this is the natural way when we write mathematical formula. But then when it comes to compilers, translating your program or how you write, you can read naturally into what machine will understand. Usually we'll translate it into the postfix notation, which will be processed more easily into machine code. And so the evaluation is like this. You scan the expression from left to right, which is what we're doing here. And then when an operator is found, and then you back up to get the operands, and then perform the operation, and then you continue. So here's a more concrete example with you know, a simple, let's say we have, now let's read this together before we understand how it's going to work, how we're going to implement this with the stack. So with this expression, so what we're doing here is 6, 3 plus. So we need to do an addition with this two numbers. So 6 plus 3 equals 9. So you think of this three things here is 9 now. 2, multiplication. So 9 times 2, the end result is 18. Now, equal sign is also operator. Essentially, this is a terminating operator here. Once you recounted this, the expression is done. You need to evaluate, and this is no more. So the stack is very suitable for this. So what we do here is, first, you want to push 6 into the stack, push 3 into stack. Now you have seen the plus operator. So what you're going to do, you're going to pop these two values off the stack, and then you do the operation, you evaluate the result, which becomes 9. You push that into the stack. Now we're going to encounter another operand, 2. Now push that in the stack. Now we see a operator, multiplication. So then we'll do the calculation by popping these two values off the stack, and it will do a multiplication, becomes 18, and 18, push that onto the stack. And then we continue to scan the expression, we see an equal sign. And that means that's the end of it. We just pop that off and print it out. In our little example, let's assume we're gonna only use the arithmetic operators. And then, you know, once we encounter a symbol equal sign, the expression ends. Now, if the symbol is anything else, that's basically a invalid condition. Now, we're also gonna make an assumption here. So in this particular programming example, we're gonna use a pound sign. And then when we see a pound sign, we know there's a number following. Now, if we don't see a pound sign, and then we know it could be an operator or an equal sign. Now, if there's something else that is invalid. So the main algorithm is very simple. So we're going to scan this whole expression. We read the first character, and I'm going to loop through the whole sequence of characters. Inside this loop, now the ending condition is we still have more characters to read from the expression. Now inside this, we're going to you know, get the stack initialized and process the expression and output the result and evaluate the next expression. essentially assuming we have multiple expressions here. So this is to process all the expressions. So we have a couple of functions that defined to process this. Evaluate expression. This is to evaluate each postfix expression. The expression ends with an equal sign. So we want to get data from a input file stream, and then we want to write the output into another file stream. Evaluating the operator, essentially that's where we do the calculation with the operands, and then handles error conditions. Now, if there's an error, we want to discard the rest of the expression. So we're going to just basically discard all the characters until we see the equal sign, and we're done with this particular expression. Print the result is essentially just to print out the eventual result if there's no error. Otherwise, we'll just show some error message. Now, that is one example, and the code is provided in the goodie bag. Now let's look at a second example of using stacks. Let's say we have a singly linked list. We want to print out the linked list backward from the very last element to the very first element. Because a singly linked list, we do not maintain the pointers going backward. So how do we accomplish this? Well, we can do this with the help of a stack. Now, to handle this, because we're scanning a linked list, and we could use a linked implementation of a stack. So here's an example. So say we have a linked list like this. We want to print out the elements from, backward. Print out 15, 10, and 5. So what we do here, we're going to initialize a stack, make a current a pointer variable called current. And then for each current element, we're going to push that on the stack. So 5 was pushed on the stack. And we're not pushing the value, we're pushing the pointers, by the way. So that was the pointer to the element with the 5 element value. And then we just iterate over the list, move on to the next, and they're going to push 10 into the stack, while the pointer that goes to element 10, and then we're going to push element 15, basically the location, the address of that element into it. Okay, once that is done, now we're going to start. I'm going to start the output process by, essentially, if you look at this, now we can pop this element off. So the last element that went on the stack, it will be the first one that comes out. Now essentially we're scanning the list backward by doing that way. So we know exactly where the last element is located because the address is remembered here. And so we're going to pop this element off. So that is popped off, and then we're going to move on to the next element, 10. And then move on to the next, pop this 5 off. And then this current pointer goes back to the very first element of the list. So essentially we did a reverse traversal of the list with the help of a stack. That's the end of the lecture. Thank you.